All right, welcome to 1.4, Composition of Mixtures for AP Chemistry. All right, let's get into it. So really the only equation you're going to need to know is the stoichiometric map. Now, I had shown you in 1.1 a little stoich map that you could use, and if you want to pause the video again, you can and write all that down. This is mass of the given to mass of the want or unknown, but I also put this little map in there for you. If you give me a second, I will zoom this in real quick, and you can kind of see how if you go from grams to moles, you have 1 mole of that substance over the molar mass of that substance, so molar mass goes on the bottom. So you can use this map as well, but we're going to be using stoichiometric relationships in several of these problems. Okay? All right, let's go over the notes. A couple of things. Not only the stoichiometric map do you need to know, but you need to also know how to calculate mass percentage of a substance in a mixture. And that is this right here. You're going to take the mass of the substance divided by the mass of the total mixture times 100 to get the percent mass of that substance. So that would be the other equation that you need to know from these notes. Okay. Now, elemental analysis is to determine the composition of a mixture, and it can be qualitative. In other words, what are all the different elements, the properties of those elements, or it could be quantitative, which is actual amounts in grams or percentages. Now, there's 2 ways we do elemental analysis. There's CH&X, but that's mostly for organic chemists, and that's to calculate mass fractions of various elements by using combustion analysis. You will not be doing that in AP Chemistry. The one that we kind of focus in on is spectroscopy, and we really look at mass and photoelectron. And if you look, 1.2 is all about mass spec and calculating the average atomic mass with a mass spec graph or data table. And in 1.7, we'll talk about photoelectron spectroscopy. Okay. Now, when we get to Unit 3, there is optical spectroscopy. And we will be doing that lab where a laser light is passed through a colored solution, and we talk about light absorbed and transmitted and how we find the concentration of the solution. So those are really the 3 main ways that we do it. This one is through a graph, this one is an actual lab, and then this one is also another type of graph. Okay? And that's how we figure out the composition of mixtures. Now it really gets into, well, what if we want to calculate it through math, through stoichiometric relationships? So that leads us into the I do and we do. So I'm going to take this and put it off to the side. And I'm going to just zoom this in just a little bit to get the I do a little bit bigger. All right, so we have aluminum metal, and it is reacting with air, and that forms a thin layer of corrosive resistant coating called aluminum oxide. And what happens is, here's the unbalanced equation. So you get aluminum reacting with oxygen to make aluminum oxide. So we have a sample of a mixture, and that sample weighs 120.91 grams, and it was analyzed. And the total mass of the aluminum in the sample was 120.32 grams of aluminum. So here's the mixture mass, and here's the mass of just the aluminum. All right, the first thing is A says write the balanced chemical equation, because if we're going to use stoichiometric relationships, we have to have a balanced chemical equation. So I'm going to put in lines for the coefficient and rewrite this. Aluminum solid plus oxygen gas forms aluminum oxide solid. All right, so let's deal with the oxygen first. Since it is in a compound form, whatever we do to the oxygen, it's going to affect the aluminum. So we have 3 oxygens here and 2 here. Well, the common multiple there is 6. So if I put a 2 here, that gives me 6 oxygens and 4 aluminums. So I gotta come over here, 2 times 3 gives me 6 oxygens, and then I just put a 4 in front of the aluminum, and now we're balanced. Now, B says, what's the mass of oxygen that was in the sample? All right, so remember, the sample mass is 120.91. The aluminum mass, just the aluminum, was 120.32. So if this is 120.32 and this is 120.91, by subtracting those two, we'll get oxygen. So let's do that math. So 120.91 grams minus 120.32 grams, and we get a total mass of oxygen as 100.59 grams of just the O2. All right, now, what is the mass of aluminum oxide in the mixture? Well, this was the total mass. This was the mass of just the aluminum. And if you add this mass with this, you get back to this. But it wants to know what the mass of aluminum oxide is. Now you might think, well, aluminum oxide is this minus that. Well, we got to use a stoichiometric relationship. So I'm going to use this mass of oxygen as my given over 1. And then I'm going to go from mass of oxygen to mass of aluminum oxide. So I am doing this step. So I'm going to do the molar mass step to get to moles of the given, use the balanced chemical reaction to get to moles of unknown, and then molar mass of the unknown to get to mass of the unknown. Okay. So let me plug those values in. So 1 mole of O2 is 32 grams of O2. For every 3 moles of oxygen that react, 2 moles of aluminum oxide can be produced. And then for every 1 mole of aluminum oxide, we have the mass of aluminum oxide. So if I take 2 aluminums and 3 oxygens and add the masses together, I get 101.96 grams of Al2O3. Now I check my stoichiometric relationships. Grams of O2 cancels, moles of O2 cancels, moles of aluminum oxide cancels, and I'm left with grams of aluminum oxide, which is what I want. So when I multiply across the top and multiply across the bottom, then I divide, I get a total of 1.3 grams of aluminum oxide in the mixture. So now we have the mass of the aluminum oxide, and it says what's the mass percentage of aluminum oxide in the aluminum and the aluminum oxide in the mixture. So this is the total mass of the mixture. So 120.91 grams. We know that 1.3 grams was this. So if I subtract those two, I get the mass of aluminum. So 1.3 grams gives me 119.6 grams of aluminum. Now, if I take this mass, which is the mass of aluminum oxide, 1.3 grams of aluminum oxide, divided by the total mixture times 100, I get the percent of aluminum oxide, which is 1.1% of aluminum oxide. Here, I want to find the mass percent of aluminum. So I take 119.6 grams of aluminum, divided by the total mass of the mixture, times 100, and I get 98.9% of aluminum. And if you take that and add it to that, you get 100%, which would add up to the total mass. All right. Now let's look at the we do. Now again, you have the video that you can watch, but I'm going to go ahead and walk you through this. It says you have calcium carbonate reacting with acetic acid to form water, carbon dioxide, and calcium acetate. So if we have 4.421 grams of carbon dioxide was produced from 10.57 grams of eggshells, what percentage of the mass of eggshells was just the calcium carbonate? Well, we got to kind of do a couple of things here. First, we're only given the mass of carbon dioxide. This is the total mass of the eggshells. We want to find out how much of the eggshells is this. So since we're starting with carbon dioxide and we have a clear stoichiometric relationship, we can start with that and convert grams of carbon dioxide into grams of calcium carbonate, and then use that mass of the calcium carbonate and the total mass of the eggshells to find the percent of calcium carbonate. So like part A is going from CO2 to CaCO3. So 4.421 grams of CO2 over 1. And we've got to know the molar mass of carbon dioxide, because 1 mole of CO2 is the mass of CO2. So when I take 1 carbon and 2 oxygens and add them together, I get 44.01 grams. Then the mole-to-mole relationship. So for every 1 mole of carbon dioxide that's formed, 1 mole of calcium carbonate has to react. CaCO3 to 1 mole of CO2. And then 1 mole of CaCO3 is the mass of CaCO3. So when I take 1 carbon, 3 oxygen, and add that to 1 calcium, I get 100.09 grams of CaCO3. All right, so grams of carbon dioxide, moles of carbon dioxide, moles of calcium carbonate, and I get mass of calcium carbonate. So once I have that mass, that's the mass of just the calcium carbonate. Now I can relate it to the eggshells. So when I multiply across the top, multiply across the bottom, and then divide, I get 10.05 grams of CaCO3. So then part B is the mass percent of CaCO3. So we take the 10.05 grams, we divide it by the total mass, which is 10.57 grams times 100. And when we do that division, we get 95 point. Let me double check that. I just want to make sure that that's not higher. 10.05 divided by 10.57 times 100. No, we get 95.0804. So we're just going to round that to 08% of CaCO3. Okay? All right, now with the you do, I did give you room to work on the problems. However, if there's not enough room, please do your work on a separate piece of paper and then just put your answers on the content worksheet. So let's look at questions 1 through 6, and I'll give you some hints on how to solve. So you're starting with a total mixture mass of 15 grams for the sample. We give you 6.35 grams of sodium carbonate, but we want the mass percentage of sodium hydrogen carbonate. So this one is just like the we do. You got to convert this grams of sodium carbonate into the mass of sodium hydrogen carbonate, and then take that answer and divide it by 15 times 100 to get the mass percent. All right, for number 2. Number 2, it's a throwback to physical and chemical properties. So what do you know about sand, salt, and iron fillings? What physical and chemical properties can you think of that if you had sand, salt, and iron filings in a, let's say, beaker, how would you get the iron out? How would you get the salt out? how would you get the sand out? How would you separate those three things to be able to take the mass of each individual part and then calculate mass percentage? It doesn't say that, but that's essentially what that problem is for. If you had a total mass of, let's say, 10 grams, how many grams is the sand, the salt, and the iron fillings by separating it? Okay. All right. Now, for question number 3, we've got I was off camera. We have a sample of brass. Brass is an alloy that has copper and zinc in it. The zinc alloy was reacted with so much hydrochloric acid according to the following balanced chemical equation. So with that, after the zinc reacted, the mass of the remaining solution was 36.309 grams. So we've got a sample of brass and we've got the solution. So what was the mass of the hydrogen gas that was produced? What was the mass of the zinc that reacted? And then finally, what is the percent of zinc by mass of the alloy? So we can look at this a couple of different ways. You've got a couple of different sample masses here, so you've got to be careful. What do we start with? Well, let's look at the final question. It's asking, what is the mass percent of zinc in the alloy? So the first thing I would do is for number A, what was the mass of hydrogen that was produced? Well, we know the mass of the reactants, right? We have 1.230 of the brass. That is the total mass of the brass. That includes the copper and the zinc. And we have 36.309 grams. Well, you have to look at what are we going to do to just get the mass of hydrogen. Would we use the 1.203 or would we use the 36.309? Well, you have to consider, how do we get as high as 36.309 grams if the sample of brass, including zinc, is just 1.203 grams? So that hydrochloric acid had to be 35.123 grams, because when you take that and add it to the 1.203 that includes the zinc, you get 36.326 grams for the reactants. Then what you can do is subtract 36.326 grams of the reactants from the total mass of the solution that still weighed 36.309. That would be the zinc chloride solution, the aqueous solution. When you subtract those two, you get the mass of hydrogen, which is going to be pretty small. And then for part B, you take that mass of hydrogen and convert it into mass of zinc. And then once you have the mass of zinc, you just divide it by 1.203, the alloy, times 100 to get the mass of zinc. Okay, so you have the alloy, which is 1.203 grams, and it's reacting with hydrochloric acid. Well, hydrochloric acid, if you add chlorine and one chlorine and one hydrogen together, you get 35.12. Okay, depending on what you're looking at as far as periodic tables. So you get a total mass of 36.33 or 326 for the reactants. So you subtract that from the solution weight of 36.309 and you'll get your mass of hydrogen. All right, number 4, you're reading A and B and you have to justify sodium, the percent of sodium being higher or lower in that sample of salt, and then sodium in sodium iodide. You've got a sample of sodium bromide that has a mass percentage of sodium of 22.34. Well, how do you get that? Well, you've got 22.99, which is the mass of sodium, divided by the total mass, which is sodium plus bromine, times 100 gives you the mass percent. So you got to do that. 22.99 divided by the total mass of NaCl, and then 22.99 divided by the total mass of NaI. And then you should be able to justify your claim by knowing if sodium is going to be higher or lower with chlorine or higher or lower with iodine. All right, number 5, a mixture consisting of only lithium chloride, lithium carbonate, and lithium nitrate was analyzed. The elemental analysis of the mixture revealed the following. So you've got these percent compositions, and you've got to use those to be able to calculate the various things that were analyzed. So you got lithium, you've got chlorine, and then lithium with carbon and oxygen, and then lithium with nitrogen down at the bottom and oxygen. And it says calculate the mass percentage of each compound in the mixture. So you're going to assume that there's 100 grams total, so each of those percents becomes masses. So if we want to analyze all the chlorine from lithium chloride, you're going to take that 10.56%, convert it into percent, take that and convert it into mass of lithium chloride, and then take the mass of lithium chloride that you get, divide it by 100 grams by the mixture times 100 to get the mass percentage of lithium chloride. You're going to do that same thing, that all carbon is coming from lithium carbonate, so you take that percent of carbon, turn it into mass of carbon, go through the stoichiometric relationship of going molar mass of carbon, then the mole to mole ratio, and then the molar mass of lithium carbonate to get the mass of lithium carbonate. And you divide that by a 100 gram mixture to get the percent mass of lithium carbonate. Then all the nitrogen comes from lithium nitrate, so you're going to take that mass of nitrogen, 10.01, convert it into grams, so you got 10.01 grams of nitrogen, and then go through the stoichiometric relationship of molar mass, mole ratio, and then molar mass of lithium nitrate to get grams of lithium nitrate, and then you'll divide that answer by 100 grams to get the percent of lithium nitrate. Okay. All right, and then the last one, number 6, can be a little tricky, but I want you to take what you did for 1 through 5 and try to answer A, B, and C. Now, empirical formula was from the previous 1.3. You got to find the molar mass of the compound. So this is your molecular mass. So you got to find the empirical formula to get the empirical mass, divide those two to get the molecular formula, and then calculate the mass percentage. So you're going to use 1.3 and 1.4 to help you answer 6. Okay? All right, so that is your notes and review of 1.4 composition of mixtures, and I will see you in class.